Okay, so it's time to go ahead and begin today. So during today's lecture, and probably I would say for the rest of the quarter when I talk about any piece of hardware, it would be good for you to have this diagram on your computer or one of our computers, just so see it more clearly. I know when it projects up on the screen, the resolution's not the best, so you probably can't make out some of the smaller numbers. Okay, but from here on out, pretty much when we discuss hardware, we're going to be referring to that diagram. So whether you look at the computer or if you still have the hard copy that I gave, I think during the first week, it'd be good to have that. So today's lecture and your next assignment is to build the reg file. Okay, this module right here. If I remember correctly, I think your second software assignment's due tomorrow. And then this will be due next week. But before I talk about the reg file, and we talked about it a little bit, but we're gonna, of course, talk about it in more detail this time. But before we get to the reg file, there's just a few things I want to review, namely the other hardware that we talked about before we go into more detail about the reg file. Okay, so remember, we talked about the program counter. In fact, you built that, right? You already modeled that in System Verilog. So tell me again, what the purpose of the program counter is. Like, what is it outputting? The address of what? The instruction. That's what the output of the program is, the address. Instruction. Yeah. Okay, so when you look at this diagram, right, there's the output of the program counter. And as we pointed out in an earlier class, if you look at where the output of this program counter is connected, it's connected to this address one input of this memory module. Okay, so just kind of note that for now. We'll come back to it. But also, it's important at this point just to kind of get an overall picture of where some of the other inputs to our program counter and also the mux that goes with the program counter is connected to. So, I might have pointed this out earlier, but I think it's good to go over it again. That if you look at where the reset for the program counter comes from, it comes from an output from this control unit FSM. So, just kind of note that. Also, the PC write for the program counter comes from the control unit FSM. It's right up there. In fact, if you look at the majority of the outputs for this control unit FSM, it's things like reads and writes. Okay. Now the PC sort that goes to the select of this mux for the program counter, that's an output of this control unit decoder. And again, if you look at the outputs here of the control unit decoder, you'll see that they're all selects to muxes. Now there's this one here, ALU fun, that goes to this ALU, but next week you're gonna see that this ALU is basically a big mux. Okay, so, your control unit FSM is controlling all the reads and writes basically, and also that reset. And then the control unit decoder, it's controlling the select inputs to the mux. And remember, the select input to the mux determines which input of the mux gets connected to the output of the mux. And you're gonna see also next week, starting next week, that the mux is basically controlling how the data flows through the microcomputer. Okay? That's kind of like just an overall picture sort of thing. But more specific, if you have to do this when you built the program counter, reset and PC write, are they active low or active high? Active high. In fact, again, I mentioned this earlier, just in case you missed it. All inputs for all the modules in the Otter are all active high. Okay, we don't have any active low. Okay, they're all active high. Okay, how about the reset PT right for the program counter, are they asynchronous or synchronous? Synchronous, right? We should have went into an always FF block, right? In fact, all inputs except one, okay, all inputs except one, in the order are synchronous. There's only one that's asynchronous, and it's gonna come up today, okay, but everything else is synchronous in the order, okay? All right, we talked about PC source, that's just coming from the control unit decoder, to the select of the mux for the PC. But then also notice, these inputs to the mux for the PC. You know, we got this input here, that's gonna be, the program count plus 4. And then we have another input that's JALR, we got another input branch, we got another input JAL. Now there's two others here, MPVEC and MEPC. I don't know if we're gonna get to those this quarter, they have to do with something called, interrupts. But, you know, we're definitely gonna get to the rest of this. And if you look at where JALR and branch and JAL, those inputs, if you see what, if you follow to where they're connected to this thing called a branch address generator. Okay. You know, and again, in about a week, or a little bit more than a week, you're gonna build this, okay? But right now, just think about what you've already learned. When you were doing the last software assignment, or when we were talking about it last time, and even when we were doing the program of the prom, there was the JAL that had that immediate, that has to be a label within RARs, right? And then with any branch instruction, there's also an immediate that's got to be a label when it's in RARs. But we talked about that it's really a number, and that number provides an offset to the program counter. Okay, so you see, having some knowledge of the software now, it should kind of make sense that, you know, there's gonna be something going to this mux that's gonna output to the program counter that has the address of the instruction that's gonna be executed, right? Because if we're not going through the program sequentially, right? If we're not going, you know, instruction by instruction, every foreign address, if we're gonna jump or if we're gonna branch, well, we need some way of altering the output of this program counter so it doesn't go in increments of 4. Okay, like it maybe goes 80 or goes 20. It's got to be some number divisible by 4, but not equal to 4 as you're going sequentially through. Okay, and notice that this branch address generator, right, that's spitting out, you know, outputting to the mux that goes to the program counter. Notice that it's also connected to something called an immediate generator. Right? And you've seen in your instructions, there's those numbers that we call immediate. Right? Well, here's the hardware that generates those numbers. Okay? So the reason I take a little bit of time right now and kind of give you an overview is hopefully, if you haven't already started to see it, hopefully you start to see that the hardware and the software, they're intertwined, right? To understand the software, to understand why the instructions are the way they are, you have to look at the hardware. To understand how the hardware is connected, you got to understand the software, right? It's all intertwined, okay? All right, you know, we're going to get into more detail, right? But this is kind of like the overall kind of view. Okay, so let's see. Well, actually, you already told me this, that these are active high. We answered this already, active high and synchronous. Okay, so any questions on the program counter at this point? One other thing, let me say just real quick that I mentioned before, but again, it's important. Since we always start with the first instruction in our program, we always start at instruction address 0. When you go to build this FSM in about a month or so, it'll be a while until you get to that. But back in 133, remember, anytime you do an FSM, you need a state diagram. Well, you'll see that when you do the state diagram for this FSM, in its first state, you're gonna reset the program count. You're gonna make this reset high. And once it gets its first clock edge, right, because it's synchronous, we're gonna reset that program counter and put the address of the instruction to be executed as a 0 going into the memory module. So we start with that first instruction in our program that's at address 0. Okay? Okay, all right, so that's the program counter. Now let's talk about the memory module. Okay, that's this right here. Now the memory module, we actually provide to you. Okay, Dr. Hummel designed this, so you're not gonna build the memory module. That's given to you. Okay, but we talked about how the memory module has these different segments. Right, there's the code segment, the data segment, the stack. Remember, there's also an MMIO, right? The memory mapped IO, but that's outside the memory module. Think of it as external data, right? That's where the input output data is, and that's external to the memory. So code, that's where your program is. And then what physical device is like within the memory module where the code is? Like that's what we learned to program a week or so ago. Program, right? So the program is within the memory module. And so within this memory module is the program. Okay, like the program is like a sub-module, if you will. Okay, so remember, that's where the program is. It's in the program. Okay, and then there was a name that we called these segments here. Okay, all these segments except for the memory mapped IO that wasn't included. Do you remember there was a name we called this? Because this is the portion of the memory that's actually located in the FPGA of the basis board. It was given a name. Real memory. Yeah, it's just called real. And the reason why it's called real memory in this instance is because the limitation of address from 0 up to, I think it's all, is it all F's? I can't remember. Let's look at the, I think it's 4 0. Yeah, because the whole thing is 8 F. So it's 0 0 0 0 then 4 F, right? That's right here. That's not right. But we can look at the manual, verify. Can you verify for me? Is that what this address of the stack is, the last? It is, okay, see some people shaking. So yeah, again, this 0 0 0, FFFF, that's set by the hardware. That's a hardware limitation. Maybe some are just right, limited by the FPGA. If we had a different developmental board that had a different FPGA, that could be a different number. Now, the other addresses you see, like this address here from 0 to 5 FFF for the code portion, the programmer set that. Okay, and likewise, the address range for the data, the address range for the stack, that's set by the programmer. In this case, it was set by Dr. Hummel. Okay, so that could be altered, but this can't be altered unless you get a different developmental board with a different FPGA. Okay? Okay, but see, I only wrote this address here down because this is the one I kind of want to focus on, because one of the things you might notice, and actually somebody last class pointed this out, is that here we have the address of the instruction to be executed. And how many bits is it? 32 bits. But here, address 1, this input to our memory module, it's only using bits 15 to 2. See, it's not using all 32 bits. Can you think of a reason why? If you look at that diagram and look at the address range for the code segment, do we need 32 bits to represent 0 0 0 0 5 FFF? No, because half of them are zero, right? Also, can you think of a reason why we're not using the 0th bit in the first bit? We're not using the least two significant bits. In fact, if you were to look at the code that Dr. Hummel wrote for this memory module, you would see that he set the 0th bit in the first bit for this address one, he set them both to 0.
It's gonna like kind of skip those when it changes because it's going up that for everything.
That's exactly right. The instruction, remember, this is this output of the program counter going to this address one. It's the instruction of, or the address of the instruction to be executed. And as we talked about, instructions are separated by 4 in address. Right, as you did in one of the software assignments, right? We talked about how if you have a binary number divisible by 4, the last 2 most least significant bits are 0. Okay, so that's the reason why we see what we see. Okay. All right, so here we are at the memory module now. Once the address has been provided by the program counter, the next thing that's going to happen is this read enable 1, which is active high, is going to be made to be high. Now, again, if you look at where it's connected to the control unit FSM. So that's the module that's making it high when it needs to be. And then since it's synchronous, once it's high and it gets that 0 to 1 transition, because again, every module in this order is rising edge triggered, right? So once this read enable 1 active high, happens on the clock edge, now at output DOut1, that's where the instruction at this address is going to be. Okay, so at the output of the program counter is the address of the instruction to be executed. At DOut1 of the memory module, that's where the instruction is. That's where the 32-bit instruction at that address is at now. That's where the data is, right? The instruction. Okay, so once your read enable is active, right, active high, and at the time the 0-1 transition, right, this just is saying that this is synchronous. Okay, so once you have that, now DOut is going to have the 32-bit instruction to be executed. Okay, so the address of the instruction to be executed is at the output of the PC. The actual instruction to be executed is at the DOut1 of the memory module. Okay. I'm spending some time on this because if I've seen in the past that if I don't spend a little time, people get confused. People think the instruction's here. And if you think the instruction's here, nothing else makes sense. Okay. Okay. Now, before we go any further with the reg file, let me just review some of the things we already talked about, and then we'll go further with some new material about the reg file. Okay, we already talked about this, but kind of skipped over this. But just real quick, we talked about this. How many registers are in the reg file? 32, right? Because if you look in your assembler manual, right, it has that table, 0x through 031. Again, some of them are special, but those are the registers that are within that reg file module. So there's 32 registers. They each can hold how many bits? 32. And since there's 32 registers, what's the minimum number of address bits that we need to address 32 things? 5, right? And again, this is where knowing the hardware helps you understand the software, because that's why when you look at an instruction that has RS1, RS2, or RD, which are registers within the reg file, that's why there's 5 bits within the 32-bit instruction, because those bits are the address bits for those registers. Okay. Are the reg file registers, are they byte addressables? No, what registers a byte addressable? Right, the ones in the memory module. Okay, so memory module registers a byte addressable. Reg file, they're not byte addressable because they don't need to be. You know, the reason why the registers in the memory module are byte addressable is because you have commands like load byte, load half word. Right, and that's where it matters. Okay, remember, what is the purpose? You know, what occurs within the reg file? Like what's happening within the reg file here? Remember? Well, look at your instructions. If you look at your instructions, you'll see that any instruction that has any sort of operation like an and, a or, an add, a compare, you know, anything like the branch where you're comparing, they'll have like either RS1, RS2, RD. Some have all three, some just have two of the three, some just have one. But any sort of operation, whatever it may be, if you're changing data in any way, it happens within the reg file. Okay, so all operations happen within the reg file. Okay? So you just put here all operations.
So then the reg file reads the instruction from memory and then does the operation. Based on what the instruction is.
We're gonna get to that. Yeah, you're right with me. That's like the next thing. Yeah, so let me just finish these reviews here. Okay, and then do you remember which reg file registers are special? Like I said, don't use them. Yeah. Yeah, 0 through 4, but we started using register 0 last class, right? So yeah, but it's register 0 through register 4. Those are the special. Okay. And we already talked about this, right? Or you told me earlier that the program, it's in the memory module, right? Because it's part of the code segment. So the program is not in the reg file. That's what defaults. If it's in the memory module, the program located. Okay. All right. So now we're going to go into some new stuff with the reg file. But before we do, like any of this, it was mostly review. Any of this review material, do you have any question on?
Why is it 5?
Oh, why do we have 5 address bits for the reg file? Does anyone want to answer that? Why is there 5 address bits? Yeah, it goes back to in CP 133. At some point, you probably saw that the number of values that you can get from a certain number of bits is just equal to the number of bits. So if you have 5 bits, you can represent 32 things. And here the things are registers. Okay. Any other questions? All right, so let's talk about in more detail now, the reg file. Well, if you take a look at the reg file, one other thing I want to mention about the memory module is, you know, all we've talked about thus far with the memory module as far as inputs and outputs is we've only talked about this address 1 input, this DOut1 output, and this RDDN1, which stands for read enable input. Later in the course, we'll find out what this address 2 is, what this DN2 is, this DOut2 is, and the other ones we haven't talked about. Okay, we're not ready for that yet. I mean, I could talk about it, but it wouldn't make a whole lot of sense at this point. Okay, so we'll come back to that. So we've only talked about the part of the memory module that's pertinent to, you know, where we are at this point in the class. Okay, now, but if you look at the reg file, okay, let's look at what inputs we have. We have an address 1, right? ADR1 stands for address 1, address 2, WA, and look, for address 1 input, we don't take all the 32 bits of the instruction that's at the output of this memory module. We only take bits 19 through 15, right? Which are 5 bits. 5 bits because we need 5 address bits for the reg file registers, because like we said, there's 32 of them. For address 2, we're just taking bits 24 through 20. For WA, which stands for write address, we're taking just bits 11 through 7. Okay, so we've got our entire instruction here that's 32 bits. but then we're parsing out just the address bits for address one, just the address bits for address two, and just the address bits for the right address. Okay, we got a clock input because it's a sequential circuit because there's registers. We got this enable input that's connected to reg write. And lo and behold, that's another output of the FSM, that's coming from the FSM. We got this input WD that's coming from the output of this MUX. WD stands for write data. And then here's the outputs. We got output RS1 and output RS2. Okay? So first of all, address 1, as you might expect, ADR1, that's the address of RS1. Right? Remember, you look at the software instructions, and some of the software instructions have RS1, right? Source register 1. Well, that's where the ADR1, that's the hardware address for that source register. ADR2, that's the address of RS2. In WA, that's the address for the destination register. Okay? Now, data is read from RS1 and RS2. Okay, so see if I can, oh, good, didn't go to sleep. So you have your addresses for, you know, your RS1, your RS2 here. Here's where the contents of those registers are going to be, right? The data that's within those address registers. So notice they're 32 bits because, again, reg file registers can hold 32 bits of data. Now, the data from RS1 and RS2, they're read asynchronously. Let me see, how can I write this? Okay, so read asynchronously and simultaneously. Right, so the data is available at these two outputs at the same time. And it's asynchronous, so it doesn't depend on a clock. So these two outputs here, they're the only, or I should say, when we read from these outputs, that's the only thing that's async in this whole microcomputer. Everything else is synchronous. Okay, this was the one exception that I was talking about earlier. Okay. Now, the data to be written to WA, the address that's at WA, that's right here. That's at input WD. Okay. So this would be the data, you know, this would be the data written to the destination register. Okay, so, you know, when you have an instruction where, let's say you're adding the contents of register 1 and register 2, well, the contents of those registers would be here, and then the result would be here, and that's what would be written into whatever register you specify as the destination register. Okay, and a write, this is synchronous. Okay, so it's a synchronous write. All right, it's single. You only have one, you only have one input for the write. You know, you can read two things simultaneously, but you can only write to one register at a time. And so it's a single write, and it's active high. Well, the enable, or I should say the enable has to be active high. See here, the enable is connected to reg write. So to make a write happen, the enable has to be 1. All right, so if this enable is 1, and again, it's being controlled by the FSM, okay, the reg write output of the FSM. So when this enable is 1 and you get the rising edge of the clock, that's when the write would happen. Again, the reads are asynchronous, so they have nothing to do with the clock. And in fact, because you cannot write to either address 1 or address 2, since you cannot write to either address 1 or address 2. So you can only write to WA, only write to the right address. So since you cannot write to either address 1 or address 2, when modeling RS1 and RS2, can use okay, so since we're never writing to address 1 or address 2, when we model the async reads here, we're just going to use assign statements. Okay, because if you remember in Verilog, System Verilog, an assign statement, it's happening all the time. See, if we had a case where you could write to address 1 or address 2, we wouldn't be able to use assign statements. We'd have to do an always FF where we have like another variable in our sensitivity list for our always FF. So instead of just looking at it at the rising edge of the clock, we'd have to look at it at the rising edge of the right for the address 1 or the address 2, okay, which you might have learned in System Verilog in 133, okay? But see, this is a different case, okay, and that's why I mention it, because this is different than what you learned in 133, okay, that if you're not writing to a specific address, well, then you can just use an assign statement to do the reading, because you would just do it all the time. Okay? Actually makes life easier when you go to model this in Verilog. Okay, so now, you know, what's around the reg file as far as like what it's outputting to, right? It's you can see that you know, RS1, RS2, that data is coming over here where the ALU is. You know, you can see that this data that's going to be written to the destination register is coming from an output of this MUX. It's got like 4 inputs. You know, all that we're not going to talk about yet because we're not really ready for that. The main thing today, I think, to take away from this is, you know, knowing what these inputs are, right? We got our addresses of our registers here. The data being read is here. The data being written is here. Right, this has to do with the destination register. These have to do with our source registers, you know, address 1, address 2, again, source registers, WA, destination register. Just kind of knowing what the inputs are for at this point is probably the most important thing. Okay. All right, so do you have any questions up to this point? Because the next thing to do is to get into how you're going to model this in System Verilog. Okay, there's some things that I'm going to go over to make your life easier than if you tried to do it with only your knowledge of CP133. You know, you're going to see quickly that in CP133 we had you do things the hard way sometimes, right? And that was just because, you know, that's an intro class, and you know, if you go right into the fancy stuff, you know, the sophisticated stuff that Verilog can do, you wouldn't appreciate it as much, right? You're going to see that we can create like a whole bunch of registers like with 1 line of code. So, all right, but before I start showing you the Verilog code that you need, and you'll need this for, you know, your next assignment. Do you have any questions up to this point? Yes. Yeah, very good question. Yeah. WA, that's the address of your destination register. That's where you're going to put the data. WD, that is the data. Yeah. Yeah, I'm glad you asked because, yeah, people get data and address mixed up all the time, so, yeah. Okay, any other questions? All righty, well, let me move the camera. Doing good on time here. And we'll start talking about the code that you need. All right, so the first thing is, I want to show you the system Verilog that we want you to use to model those 32 registers in the reg file. And you're going to use what we call an array of vectors. And I'll just give you an example here of 7, and then you can figure out what you need to do for 32. Well, I'm going to give you an example of 7 10-bit vectors, which is the same thing as saying 7 10-bit registers. I mean, vectors in this case are just equal to registers. I mean, you'll have to do 32 32-bit vectors. I'm doing an example with 7 10-bit. So all you have to do to create an array like this is to put logic and then 9 to 0. So this is going to specify 10 vectors or 10 registers. It's going to assign, or excuse me, this is going to create the number of bits that each vector has or each register has. And it's going to assign the least significant bit, the 0th bit, and the most significant bit, the 9th bit. Okay, since we want 10 bits. So this is telling how many bits for each vector or how many bits for each register. Then you put RAM. And then you put 0 to 6. Okay, so here, this is where the number of registers or vectors are going to be. So since we want 7, 0 to 6, and then it assigns address 0 to the top register, and then 1, 2, 3, 4, 5, 6 in a, going in a downward direction. So if you made a picture of this, it would just be something like this. You have 7 rows that represent, let's see, 1, 2, 3, 4, 5, 6, 7. Right, each row represents a vector or a register in this case, and then 0 would be the address of the top one. 1, 2, 3, 5. Just in the sign. Oops. 5, 6, not 5, 7. And then each vector has 10 bits. 5, 6. I think that's 10. 2, 4, 6, 8. And your least significant bit would be the 0th bit, and the most significant bit.
I think, is there a RAM that's directly around where
Yeah, it is like this. I know it's opposite, but yeah, well, if you put it 6 to 0, the only difference is gonna be is that it's gonna call this top register address 6, and this bottom one address 0. And I just, by convention, we think of address 0 in a diagram like this as being the top one. That's all. Yeah. Yeah, and likewise here, like if you did 0 to 9, the only difference would be is the least significant bit would be the 9th bit and the most significant would be the 0th bit, but that's against convention. Some of you might remember that in CP 133, that's what Dr. Mealy did in that universal seg module. Remember how you had to do everything in reverse because he did it unconventional. Dr. Mealy tends to be unconventional if you know him, so it goes against the crowd. So, but yeah, most people do it this way. All right, so it's just going to take a single line of code. Well, see, is there a semicolon? I always get syntax from. There might be a semicolon after. Yeah, I'm not sure. There might be a semicolon here, probably is. I didn't have one in my notes, but there's probably one. You usually have to end it with a semicolon. But anyway, one line of code that's gonna generate your reg file registers. Okay, so remember in 133 when you have to do each register with like D flip-flops and then, you know, like, once you had the D flip-flop code, then you just had to use multiple bits to get the registers right. So this is a lot more convenient. All right, so that's how you're gonna create your reg file registers. Now, this is a key thing, and we talked about this a little bit last time, and you saw X0 being used in an example last time, right? I had an example where I think it was part of an add-I command, if I remember right. Okay, and that's one of the special registers in the reg file is this register 0, okay, X0. And the reason why it's called register 0 is because the contents of that register is kept to be 0. Okay, and you have to make that happen. Okay, when you model the reg file in System Verilog, you have to make it happen that the contents of register 0 are always 0. Okay, and there's different ways to do it. You know, there's some creative ways, but I think the best way, again, it's a recommendation. If you think of something else that works, by all means, again, there's more than one way to do this. But I think the best way, and this is how I did it, is to initialize all your registers to 0 to begin with, and then just make sure you never write the register 0. Okay, so in other words, you know, initialize register 0 to 0. In fact, I would initialize all the registers to 0. But then make sure you never write to register 0, because if you initialize it to 0 and you never write to it, it will never be anything other than 0. Okay. Now I'll give you the code that you can use to initialize all the registers to 0. Okay, because this is something also you haven't seen, or probably most people haven't seen in CP133. And if you know C language, or if you know Arduino, this is going to look very familiar because it's the same type of format. So this is what you can do. Right, so comment here, initialize registers to zeros. Okay, so you have an initial block. So we need to begin. And then we're going to define an integer and set it to 0. Okay, so this is just integer. I'm just using I as an integer and setting it to 0. And then we're just going to use a for loop. So in System Verilog, it looks just like in Arduino or C, the formatting of it. Like that. So it's just going to increment. It's just going to start at 0 and increment by 1, you know, up until 31, right? Because since we started at 0, the 32nd register is going to be index 31. And then we're just going to but each address just set the contents to 0. That's what this line does, right? That for each I, which is going to be an address of one of the registers, we're just going to set the contents to 0. And then go to end the for, and then end the begin. Okay. Let's see, what else do you need to know? Oh, this is important. I forgot this. I skipped over this. Sorry about that. Once you have your registers modeled, okay, with this statement right here, if you then want to access, the contents of the register or registers, or say a bit out of a particular register, the way you do it is like this. So this is off to the side here. Put like a divider. Okay, for example, if you put RAM. Okay, so that's, this is for this example that we did here with the 6 10-bit register or 7 10-bit registers. Once you have it created, if you now do this, what's gonna happen is that this is gonna take, the 10-bit data at address 0.
Oh, okay.
So see, what goes inside the brackets here is the address of the register. And then this is gonna access the data that's at that address. Okay,
Is RAM the instruction or is it like an A?
well, it's just, in System Verilog, it's sort of like a reserved word in that when you use it and, you put it in this syntax, it just knows that, you want this many registers, this many bits. Yeah, so it's just like a reserved word, that when it's recognized, the software has been designed such to treat this as, making that many registers of that many bits, that's all.
Zero W.
Sure. RAM 0 is gonna take, look, it's going back to this line here is gonna create like this picture. So each one of these rectangles is a register. Each square is like the output of a flip-flop to that register. So each one of these is gonna have data. Whatever it may be, right? Zeros and ones. So whatever number you put within the brackets, it's taking data from that register at that address, right? If I change this to 3, now it's gonna take the data from this one, right? It would be address 3. That's all. Okay. Let's see, here's another example. You could do RAM, and then it's bracket 4, and then another bracket 7. That would take just the 7th bit from register 4, address 4. So this would just take 7th bit from register 4. Okay, and then you can do things like this. You could have RAM 3, and then say you wanted multiple bits. You could do something like this. Right, where now it's gonna take these 4 bits, the 4th, 5th, 6th, and 7th bit from register 3. And then you could also do this. And say address 2. Right, you could put like a signal name in. So now it's just gonna take the data from that address that this name represents. And just like in your reg file, right, you have address 2, right? So you could use a command like that within an assign statement so that you get the data from that address at whatever particular output. Like in this case, you wanted at output RS2, right? Because that, at this output should be the data from the, the address that we have at address 2. Okay. Let's see, that was all the examples I have of that. So the last thing I have here, unless you have questions, is I'm gonna give you an outline of how to model the reg file, which is basically putting together all these things that I just went over. But before I give you this outline, do you have any questions about anything I've talked about? Everybody see what this is doing? Everybody understand? I mean, the key thing here is just understanding that in the bracket goes the address. Well, the first bracket, then here you're putting like specific bits And then you can also use a name. Okay. Okay, so the last thing here. Okay, so your reg file. Okay, so this is reg file. Oh. I'm not gonna give you everything, but I'll give you a lot of it. You just gotta fill in the blanks. So of course, you're gonna have your module name. I could probably call it reg file. Okay, and then of course, you gotta declare your inputs and outputs. You've all done that many times, so that's. Shouldn't be anything too challenging. Okay, and then after you have your model name, you declare your inputs and outputs, that's when you want to create the array. Okay, so you're gonna have something that looks like this. Okay. Right, then the next thing you want is to initialize memory to 0. Initialize all reg file registers to 0. Okay, so I gave you that. That's gonna be this block right after that. All right, now comes the async reads. And just use assign, like I said earlier, use assign statements. Okay, so you're gonna have an assign statement for RS1 and an assign statement for RS2. And that's where you're using this type of notation, right? Because if you put RAM, like if you have an assign statement, you assign RS2 to RAM bracket address 2, well, that's gonna take the data at that address and assign it to that output. Okay, so you basically just have two assign statements, one for RS1, one for RS2, where you're assigning those outputs to this notation here. Okay. All right, now comes the tough part. That, I've given you a lot of this, okay, but the one thing you're gonna have to figure out is, okay, we have a sync write, because remember we have this WA, right, and WD. WD is where the data is that we're gonna write into the destination register, and WA has the address of the destination register. So you need the code that's gonna do that synchronous write, to the destination register. And here's where you gotta think about, don't write register 0. Okay, now, well, since it's a sync write, what kind of block is this gonna have to be? Yeah, so this is gonna be an always FF block. And if you think about it, you can basically do this with one line of an if statement. Like if you think about it, now there's other ways to do it. Again, as you know, there's more than one way to model in Verilog, but the most efficient way is you have if something, this happens, else nothing. Like you would just have an if without an else. And why is that? Why would you want not to have an else within an if? Yeah, because if you're not writing, you just want it to stay what it is. You just want it to remain the same, so you want storage, so. Yeah. So yeah, if you find yourself writing a lot of code within the always FF for this, it may still work, but it's more than what you need. So, like I said, I think out of this, because I've given you, given you a lot. I almost gave you the whole thing for create array. I gave you all of this, and I basically told you how to do this too. This is the part you might have to think about a little.
So
if we, like, let's say we feed in an instruction that wants to write the address zero, how can we handle that? Like,
Well,
should we just like,
well, I think maybe what you're, referring to is that, you know, like last class, I had an assembly instruction where we were using X zero. But that instruction was, based on the fact, or counting on the fact, that register zero was all zero. Okay, so anytime that you put X zero in an assembly language program, you want to be certain that there's only zeros there. So that's what you have to make happen when you design this.
right,
Yeah.
but if, let's say someone sets, like feeds in instructions and uses, address zero as the destination register. And that, so someone's trying to write data to it, what would happen and what should we try to implement?
Well, you see, but that's the thing, is that you can prevent that from happening. In the code, you can make it such that if someone tries to write something to register zero, it doesn't happen.
But then, so is the instruction just like disregarded or does it write to a
Well-
different register?
Well, no, it's just that whatever that instruction is, it just, that part of it wouldn't happen because, you know, but so like when the person goes to C, assembles their program and goes to C, it's not gonna work the way they thought it was. Yeah. Yeah. No, you have to assume that someone might try to do it, so you gotta prevent it from happening. Yeah. You know, if someone tried to write to register zero, you just want it to remain the same. You don't want the write to happen. Any other questions? All right, well, you have the rest of today's class to work on, whatever you need to work on. Again, the software number 2, that's what's due the earliest. That's due tomorrow. I think I have this due Wednesday of next week, the reg file.